Hey everyone, I'm David. I'm the coordinator of the Maths Learning Centre, and it's semester 2, 2020, and this is a revision seminar for Maths 1B. And because it's 2020, here we are in my house via Zoom instead of all together in a lecture theatre. So I've had a few requests of things to talk about for Maths 1B, and I'll chat about those things. And when I get to the end, I'll stop. And anything I don't say, there's other revision seminars that already exist on the website that you can find about most things. And if you're at the University of Adelaide, you can drop in and have a chat at the Maths Learning Centre. Okay, so I'm going to mostly be working on my document camera. And so do please let me know if my camera is fuzzy or if I'm writing on the paper off the screen or anything like that. So the first thing I want to do is answer what someone said. Someone asked something that sounds like a quick question, so I'm going to start with that. So the question I was asked was, an orthogonal matrix, what are its columns like? So the actual definition of an orthogonal matrix is a matrix such that P inverse is the same as P transpose. That's the definition. It turns out that the only way to produce an orthogonal matrix is for the columns to be an orthonormal basis for R whatever. So it's like a theorem. I don't know what it's called. P is an or n by n matrix when the columns of P are an orthonormal basis for Rn. So the question I was asked is it okay if they're just orthogonal? No, it's not. They actually have to be orthonormal or it's not going to be an orthogonal matrix. So it would be much nicer if the terminology was it's an orthonormal matrix, but that's just not the way it is. And I don't actually know why, so I'm sorry about that. An orthogonal matrix has orthonormal columns, and that's the way it is. So does that answer your question, the person who asked that?
Yes, perfect, thanks.
Okay, right. So while I'm here, I might as well mention the whole point of wanting an orthogonal matrix is that there's two things that are useful to know about an orthogonal matrix. The first thing is that an orthogonal matrix represents a rotation. As a linear transformation, and or a reflection as a linear transformation. So rotation and or reflection, it could be both. And also, it's when you do orthogonal diagonalization, you have to use an orthogonal matrix. And so P inverse P transpose matrix P comes out to a diagonal matrix like that. So this has to be an orthogonal matrix. And that's different to ordinary diagonalization, because in ordinary diagonalization, your matrix doesn't have to have orthonormal columns or even orthogonal columns. And there's an inverse symbol here instead of a transpose symbol there. And the whole thing will only work if this is a symmetric matrix. So you can do it with an inverse, like an ordinary P matrix that isn't orthogonal for any matrix A. Well, not any matrix, most matrices, but you can only do it with an orthogonal matrix if it's symmetric. So that's all the information I know about orthogonal matrices that's worth pointing out. Does anyone want to ask any questions or say anything about that?
With that last equation, so you're saying that you can only use it if A and P are symmetrical?
No, you can only use it if A is symmetrical. So if you've got, for most matrices, you've got A and you create P from the eigenvectors, and then P inverse AP is a diagonal matrix. That's what you do for most matrices. For a symmetric matrix,
I thought we used the T and we used inverse for when it's symmetrical.
Other way around.
Okay. Other way around. Okay. Yeah.
Ordinary plain everyday matrices that aren't symmetrical and are just whatever they are, you create the P from the eigenvectors and you use P inverse AP. For a symmetric matrix A, you create P from the eigenvectors, but you also have to do the Gram-Schmidt to make them orthonormal, and then P transpose AP is a diagonal matrix.
Okay, thank you. Clear.
Very important questions to ask, because there's a lot of technical details going on there, and when things are extremely similar, it can be hard to tell which one is which. So it's very good to find ways of deciding. Yeah. So when it was first introduced, they didn't reveal the information that the only way to do this thing with the P transpose was for it to be a symmetric matrix. They didn't reveal that to the end, and it's sort of like the big punchline that says, aha, it's only possible in this situation. All right. Anything else on that? I don't know, I'm happy to talk more about it. Sweet. Okay. Excuse me. So that's that. Tick.
So just before you leave, could I just ask a quick question? Normally with the symmetric matrix, is it usually that the eigenvectors are orthogonal, so you wouldn't need to do Gram-Schmidt?
That's actually a very important question. You technically only need to do, so you're right. So if you have a symmetric matrix, then eigenvectors that go with different eigenvalues are guaranteed to be orthogonal. So just as an example, if you had A and it had eigenvalues like 3 and 3 and 5 and 7 or something, then if you had an eigenvector that went with this and an eigenvector that went with this, they're guaranteed to be orthogonal to each other. And if you had eigenvectors that went with these two, like U and V, they both went with 3, they're not guaranteed to be orthogonal. So this one, so you get these blobs, like you got a couple that are orthogonal here, and then these two are orthogonal to those two, but you have to do Gram-Schmidt inside those two to make those two orthogonal to each other. And this one you have to divide by its length, and this one you have to divide by its length. So you don't have to do the Gram-Schmidt on the whole thing. You just have to, if you get more than one eigenvector to go with a particular eigenvalue, you have to do Gram-Schmidt just within that little bit there. How do you feel about it?
Thank you. That feels better, yeah.
Yeah. So if all the eigenvalues are different and you don't get any repeated ones, then Gram-Schmidt, you just have to divide everything by its length, and that's fine. But the problem happens when there's two vectors that go with the same one. These are all excellent questions. I'm very happy that you're asking questions. It makes me happy. All right. I think what we might do is move on to some of the other stuff as well, if that's okay. Don't forget, you can always ask these questions at the Maths Learning Centre too. Okay. Awesome. Well, right. Actually, while we're talking eigenvalues, I just wanted to mention a couple of things. Eigenvalues have various properties. So I think eigenvalues is one of the coolest things ever. And they have some really cool properties that mean that they're connected to a whole lot of different things. And so what that means is that you sometimes get... Yep. You right?
Sorry, I think I accidentally unmuted.
So you sometimes get these problems where they tell you random bits of information about the trace and one column and stuff, and they ask you to find eigenvalues and that sort of thing. And that's because everything's connected to everything else when you're thinking about eigenvalues. And so there's a whole lot of information that all goes together that's good to know. And I'm just going to look it up online and show you something. Hoping very much it's on your web page. Otherwise, I'll have to find it somewhere else. My internet's being slow. In fact, what I might do is just show you something. Where's Zoom? Too many windows open. S1B. Here it is. So this is a handout that I made once, which has various facts about eigenvalues that I thought it would be useful to you to know where to find it. So there's a definition which has a v is equal to lambda v, and you're always allowed to use that. So if someone asks you to check if something's an eigenvector, multiply it by the matrix and see if it's the same as some number times the vector. And if you happen to multiply a matrix by a vector and what you get is a multiple of what you put in, then that multiple is an eigenvalue. You don't have to go through the whole process of finding eigenvalues by determinants and crap if you just happen to think of one. And then there's all of these terminologies that go with stuff. And so when you do the lambda I minus a, it's called characteristic polynomial, but when you set it equal to 0, it's a characteristic equation, and there's eigenspaces and multiplicity. And then there's all these theorems that connect everything together. So when if you've gone through the process of finding the eigenvalues, then it turns out that it's the same answer as when you add up the diagonals of the matrix. And that's always true. And I think that's one of the most ridiculously stupid things ever, that would ever be true. Like, why the hell? Like, yeah, what the actual hey, Twilight? What like that? Bleh. Why would that be true? And there are proofs as to why that's true. There are proofs as to why that's true, and there are also proofs as to why the product of the eigenvalues is the determinant. But I think that's one of the weirdest things ever. So what that means is if you know almost all of the eigenvalues, then you can figure out the last one from the trace or the determinant. Yeah. So I'm just going to leave that page there and ask if anyone has any questions or thoughts about that. No, it's not frozen. I was just waiting to see if people had something to say.
So is the trace just the sum of the eigenvalues? Is that sentence a bit contradictory?
Well, it's yeah, and so I'm going to talk about that actually. That's a very useful question. So before eigenvalues were even invented, the trace existed before that. So you just have a random matrix. Like that. The trace is what you get when you add up the diagonal. And that's it. Like it is fundamentally a stupid thing to calculate. Like if you just had a great big matrix that was all ones, then the trace would be, oh, missed one. The trace would be 4. And that's just it. Whatever is on that main downwards diagonal, if you add them all up, that's the trace. That's the definition of what the trace is. But it just so happens that the same answer, you get the same answer when you add up the eigenvalues.
Isn't there a circumstance when in the diagonal vector you make the eigenvalues follow the diagonal anyway? But that's different, isn't it?
So there is one special case, well, 2 actually. There is one special case where the eigenvalues are also the things on the diagonal, and that's when half of your matrix is 0. Oh, crap. This matrix is half 0, like it's an upper triangular matrix. The actual numbers that are here on the diagonal, they are indeed the actual eigenvalues. And so in this matrix, it's fairly obvious that if you add the eigenvalues, you get the same answer as you add the diagonal because they are the things on the diagonal. But this matrix, its eigenvalues are not. Like its eigenvalues are 4 and 0 and 0 and 0, which do add up to 4, but none of those are numbers that are actually on the diagonal.
I have a question as well. So I know a diagonal matrix is when they're all 0, above and below. So what would that matrix be if it's only half of them are 0? Is there a special name for it?
This is called upper triangular.
Oh, okay. Cool. I'll take that. Thank you.
And the one where the bottom half is where the not zeros are, that's a lower triangular matrix. It's nice to know that these things have names. Yeah. When you do row operations, and you get like an elementary matrix stuff and you multiply them all together, if you only add rows to the rows below them, you get a lower triangular matrix, upper triangular matrix, sorry. Anyway, there's this thing, you know how you did the singular value decomposition? There's a decomposition where any matrix can be turned into a lower triangular matrix times an upper triangular matrix. So not that that's relevant at all. It's just the reason why people have names for these things is that they turn up and they become useful for reasons. So.
In a lower triangular matrix, is the trace also the diagonal that's also the eigenvectors in a lower triangular?
Correct.
Or is it only an upper?
Yep, it'll work for an upper one as well. So if there's zeros all in this spot here, no matter what's here, then the eigenvalues will be on the diagonal.
If the zeros are on the bottom, would they eigenvalues be on the diagonal? So if it was the other way around?
Yep, eigenvalues are on the diagonal. If there's zeros down here, eigenvalues are on the diagonal.
Sorry, yeah.
Zeros up here.
Sorry, yeah. Yeah, all good. Thank you.
If there's zeros on both, it's still true.
Okay.
And that's to do with how the determinant works when you do the lambda I minus a. Okay. But even if the eigenvalues aren't actually the numbers on the diagonal. Whatever the eigenvalues are, they'll add up to the same answer as what these numbers add up to. So I don't know what the eigenvalues of this matrix are, but whatever they are, they'll add up to -2. That's the idea of trace and eigenvalues. So it's this grand coincidence. Maybe not a coincidence. Nothing really is in maths, but it feels like this grand coincidence that even for matrices where the eigenvalues don't live on the diagonal, they still add up to the same answer as if they did.
Thank you.
You're welcome. How do people feel about that?
Feels like I'm learning something new, which is not that comforting a week before the exam.
A week before the exam. I mean, I think the thing is it was still there. Like, it's all there in the notes. It's just that it's sometimes hard to tell because it was like 20 seconds or something in a lecture. And some things mean a lot less than they seem they mean. Yeah, so yes, that cannot be a comforting experience. I understand that, but you can also know that well, that's what the Maths Learning Centre is for, to try and fill in those things for you, to help find those things. Yeah. Okay, I'm going to move on from that. It's nice, always nice to deal with a couple of things. And while we're still on the matrix vibe, I think it would be a good idea to have a chat about these linear transformations and kernels and range and null spaces and crap. So have a chat about that. All right. One of the things that makes this confusing is that things are both similar in some ways and different in others, and it's hard to tell which one is which. And there's two sort of philosophies that are going on here, that the matrices exist. They're just things that are there, and you can do things with them and calculate stuff, and those things that we can calculate have a name. And linear transformations are a whole separate thing. It just turns out that they go with matrices, and so the terminology for matrices was invented separately to the terminology for linear transformations. And so it's useful to just look at them within their own land and then see how they're related. So a matrix is just a rectangle that's got numbers in it. That's a matrix. And I know that matrices can be pulled apart in lots of different ways. So this matrix, I can imagine it as being... Sorry, I'm just getting something out of my box of tricks. Oh, shiny. This matrix, I can imagine it as being made of columns. And I can think about what stuff I can do to columns. And if I think about it as being made of columns, and I think about the stuff that columns can do, columns are vectors, and what vectors can do is that they can span stuff. And so what I can think of is I can say the span of the columns. And that's called the column space. I will call my matrix A. And what that means is I take those columns and I produce every possible linear combination of those columns that I can think of, and not even the ones that I can think, even the ones I can't think of. I think of the idea of going something times this plus something times this plus something times this plus something times this, and I imagine all of the possible answers for that, and that all of it together, that's the column space. Everything that can be made as combinations of the columns. Cool, that's great. I'm going to leave a bit of space for the column space section, actually. Okay. The other thing I could do is that, well, matrices are also made of rows. And if I look at those rows, I can imagine doing linear combinations of those, because that's what vectors do. So if I did the span of the rows, then that would, then that would be called the row space of A, and would be denoted by row A. And it's a subspace too. I'm going to do all possible things that I can do by doing combinations of those rows. And all of those vectors together, they are the row space. Anything that I can span with these. And that's something that I could do. And the only other thing I know how to do with matrices is I could view them as part of a set of linear equations. So I could go, well, what if it was an augmented matrix and there were zeros here? Then I could solve those equations, and I could get, instead of seeing these as vectors, seeing them as coefficients of equations, and I could get a subspace that way. And that's the same as saying, if I put a vector here and I made it to come out to 0, what would go in this position here? Ax equals 0. So solution to Ax equals 0, that's called the null space of A. And it's what I would get if I saw my matrix as the coefficients part of, and I solve that. So these are three, since I know about the idea of subspaces, those are three things that I can do with a matrix to create subspaces. I can use it as a set of equations equal to 0, because that's how subspaces can be made, as equations equal to 0. Or I could use them as things to span. And there's three different things that I can do there. All right. So last thing to just mention, see this Ax equals 0 thing? I can actually rewrite the column space like that as well. If I wanted to do a combination of these columns, then I could do that by multiplying by a vector in its position. And that would give me A of the first vector plus B of the second vector and C of the third vector and D of the fourth vector. And so if I multiply this matrix by all possible column vectors in that spot, that will produce all of the answers in the column space as well. And so I can rewrite my column space as the set of Ax for all x's. Which is why in your notes, the column space is written as Ax, such that x is in R whatever. In our case, it's in R4, like that. And this one here is written as the set of x's such that Ax comes out to 0. Right, those are the three subspaces that belong to a matrix. I'm going to stop there and say, anyone got any thoughts or questions about that right now?
Are the only ones left to do the rank and kernel? like we've done the col space, the null space, and the row space. The next ones are kind of like ranking kernel one.
Yep. Yes, I'm going to talk about them as well.
Wonderful.
Yep. Cool. And I have another question. Someone has said, is it Rn or Rm? Okay, so if this is M this way and N this way, so it's an M by N matrix, then the column space is made of these vectors, and those vectors have M coordinates. So, sorry, it's like that. And this is something that's made of vectors that are in Rm. So the column space is made out of columns, and the columns have M coordinates, so the column space is in Rm. The row space is made of things with N coordinates, so the row space is in Rn. And the null space is made of vectors that are able to multiply by the matrix on the right-hand side. And so they have to have the same, if I'm going to put a matrix in this position, a vector in this position here, it has to have N coordinates so that you're able to multiply it. So the null space is in Rn. Okay, cool. So we've actually, moved on a little bit. You can say, oh, cool. So we can think about this. Where, how big are these matrices, these vectors? How many coordinates do they have? What does that mean? We can start asking ourselves, sure, it's the span of the columns, but I might not need all the columns to do that. Which columns do I need to span all the rest of the columns as well? And that's when I'm starting to talk about a basis for the column space. This column space is linearly dependent, not dependent, oh, sorry. These vectors are linearly dependent. You can't say dependent about a subspace. These vectors are linearly dependent. And so if I want to span whatever it is that these vectors span, I don't need all four of these to do it. 3 of them will probably be fine. And those 3 would be the basis for the column space. So even before you go on to that, a way of finding a basis for anything that's a span is to row reduce what you've got and figure out where the pivots came from. And that will tell you which of the original columns were a basis for the span of all of the columns. Alternatively, if you want to find a basis of things that are rows, you just do row operations and pick out the non-zero rows. And that'll do it too. Because row operations are really linear combinations, and you've just done linear combinations of linear combinations of linear combinations, which is what spanning is. And so it doesn't change what the span is. And if you want to find out a basis to something that's solutions to linear equations, you're going to have to chuck all the free variables in. And so it turns out that you can get all of the basis for these things from the reduced row echelon form. So if you've got your matrix A and you get your reduced row echelon form, and it has pivots wherever it has pivots, just imagining my vectors here. I know that this matrix doesn't actually produce this answer, but it's just an idea. So you've got a matrix A and it's got whatever, and maybe its reduced row echelon form was this. What you'd do is you'd say, look for the pivots, and there they are, and go back to the original, and those 2 are a basis for the column space. Because the column space is about the original columns and which of them are independent. And which of them end up with pivots is the ones that are independent. Okay, row space is about the rows. Because you've done some row swaps and stuff, there's no way of guaranteeing that these match with the original rows, but that's okay because the actual final rows where the pivots are, they are a basis for the row space. And then finally, if you chuck in your 0, 0, 0 and do free variables, so that you end up with like S of something plus T of something, they are a basis for the null space. So those are the 3 basises bases, I guess, that you can find from doing the reduced row echelon form of a matrix. Yeah. So the column space basis belongs in the original columns. The row space basis is in the final rows. And the null space, the vectors in the null space aren't even in the matrix. They live next to the matrix here in the definition. And so you have to create those vectors yourself from the free variables. So I've just had a question here. However many vectors are in the basis, that's the dimension of the thing. Correct. So in this particular example, the column space and the null space and the row space all have dimension 2, but that's a coincidence. So yes, if I had only had one of these here, then the null space would have dimension 1. If I had had 3 of these vectors here, the row space would have had dimension 3. Does that answer your question? And that goes all the way back to Maths 1A with the well, maybe it wasn't in Maths 1A. Anyway, the definition of dimension is the number of basis vectors that you can find. So these 3 objects, the column space and the row space and the null space that you create from this matrix that are bigger than just these vectors, it's the span of them, you can find the dimension of stuff. So, and that's a really good point, actually. You said that however many vectors the basis has, that's the dimension. Well, since the pivots tell you which columns or which rows are the basis, the number of pivots is the dimension of the column space and the dimension of the row space, guaranteed. And the number of free variables, that's going to be the dimension of the null space.
David, could you repeat that? I didn't quite get all that.
So the number of pivots is the dimension of the column space.
Oh yeah, I'll write that down.
And it's the dimension of the row space as well. And the number of free variables, that's the dimension of the null space. And that works out every time because the pivots tell you which ones are the basis. And so however many pivots are is however many there is in the basis for these 2. And you create the null space from the free variables, and each free variable will go with a vector, and that will produce the basis for the null space. And so the way the language works is the dimension has to be, when you say a dimension, it has to be the dimension of something. And in this case, it's the dimension of the null space or the dimension of the row space or the dimension of the null space. It's not the dimension of the matrix. The matrix doesn't have a dimension. Only subspaces can have dimensions. And if you span something, you always make a subspace. And so you could say it was the dimension of the span of the columns if you wanted, but that's why we have the word column space, so that we don't have to use a sentence with 2 ofs in it. Cool. Some of these little quirks of the way you talk about these things, the language stuff, is actually really hard to pick up just by listening to it. Human beings are really good at picking up language just by listening to it when they're, 1 year old. But we tend to lose that ability when we're older, especially when we're also simultaneously trying to learn maths theorems. And so the language can really get in the way. So it's always a really good question to ask about how you're allowed to say things. Yeah. So never be embarrassed to ask that question, because it's normal to not pick that up straight away. So these are all the things that belong to the matrix. All of this came about from us looking at the matrix and going, okay, what sorts of ways could I make subspaces out of this matrix? I went, I can see them as vectors in two ways, and the way to make subspaces out of a list of vectors is to span them. Or I could see them as equations, and the way to make subspaces out of equations is to solve them. And so these are the natural ways to try and make a subspace out of a matrix, which is lovely. That's all great, excellent. Okay. The problem is that matrices are also capable of doing something else. Matrices aren't just lists of numbers. They're not just collections of vectors or coefficients of equations. Matrices are also capable of producing a linear transformation. I'm just going to talk about that separately for a second. So a linear transformation is any function that takes vectors in and spits vectors out in such a way that this. So f is a function that takes vectors with n coordinates in and spits out vectors with m coordinates. And it's not like they're always 4 and 3, but I'm just pointing this out. I'll get back to that question. So linear transformation here. And it's called linear when if you add things together before you put things and you add them together and you get an answer. If you figured them out first and then added them together, you would get the same answer. And so what you normally see this as is f of u plus f of v is the same as f of u plus f of v. But the idea is that if you calculate it separately and then add them, you get the same answer as if you add them and then calculate it. And the same thing goes for this. F of any number times vector is supposed to be exactly the same thing as if you figured out first and then times it. That's a linear transformation. And these things existed before matrices. Like before people had thought of matrices, linear transformations were a perfectly acceptable thing to think about before matrices were invented. And people thought about them as sort of just transformations of the plane. Something like where, you know, you squish everything inwards or you rotate stuff or whatever. Some transformations, if you add the vectors first to get this answer and then rotate, you'll get the same answer as if you rotate them and then add them. And that's what linear transformations were all about. But then it turned out that once we thought of what matrices were, it turned out that every linear transformation can be represented using a matrix instead. So even though some of them had some wicked formulas or just a word description of like project this onto this and then multiply it by 4, or you know, you can describe linear transformations with words about what they do, and you can describe them with formulas like this, you know, f of x, y, z, t is x plus y, 2y minus t, z plus t plus 5x, or something like that. Some wicked formulas like that. And there are other formulas that you could do. I mean, there's nothing stopping you doing x squared plus y squared or y times x or the square root of z. But that won't produce a linear transformation. It'll only be linear if these look like linear combinations. It turns out that every linear transformation, no matter how you think of it, as long as you're sure that these rules work, you'll be able to rewrite it as matrix times vector. And it will produce the same answer as this. So a rotation, it's possible to rewrite it so that it looks like a matrix. So that turned out that way. But even before matrices were thought of, you could still ask some really important questions about the linear transformations. So the linear transformations, there's some really useful questions you can ask about a linear transformation. You can ask, what are all the answers that it produces? In fact, these are the same questions that we used to ask about ordinary functions. We used to have functions like x squared, and we'd ask what's the domain and what's the range and where does it cross the x-axis? Like when does it come out to be equal to 0? That's where it crosses the x-axis. And we're just going to ask the exact same questions. So we can ask what's the range? And the range for ordinary functions is the same as the range for this, which is what are all the answers? The range is the set of all the outputs, which means it's all the things that are f of x. If you take all the x's and you figure out what f of x is for every x and you collect them all together, then that's the range. Everything that comes out of a linear transformation. I can see the question that's there in the chat, and I am getting to that. So if you did a rotation, then everything that comes out, every point that comes out when you do a rotation, well, you can produce everything by rotating the plane. But if you squished the plane together, if you took a plane and you squished everything onto a line, then the range would be that line. And there are some linear transformations that don't just act inside R2, they change R3 to R2. So if you took a photograph with a camera, it would turn 3D space into 2D space. And the range is what's in the picture. That's the range. So the range is everything that you're able to produce by sticking things through the linear transformation. The other thing you could ask yourself is, just like with old functions, we asked where they cross the x-axis, which was the same as asking when is the answer 0, we could ask that too. That's the kernel. All the inputs that produce the answer 0. That's the kernel. The set of all the x's in Rn such that f of x is 0. That's the kernel.
David, what does that say before the 0? It says
answer.
Answer. Sorry, yeah, I just couldn't make it out.
That's all right. I should be slowing my words and my writing down. I joke that this is why I'm such good job. I do such a good job of teaching medical students. Because my writing is doctor's writing. These are the same questions we used to ask about ordinary functions. So we're asking them now about functions that take vectors in and spit vectors out. And so in order to answer the question of what's in the kernel, we would solve this equation. We would get the f of x and we would find out what those answers are, and we would find out which x, y, z, t's or whatever produce the answer 0. Okay, so it's important language-wise to know that a matrix has a null space and a linear transformation has a kernel. Okay, and here's the magic trick. Because the range, because the linear transformation can be thought of as having a matrix, we can create the linear transformation as a matrix instead. Oh, running out of paper. We can create the linear transformation as a matrix instead if the formula for doing f of x is to multiply x by a matrix, then it turns out that the kernel of the linear transformation is the same thing as the null space of the matrix. So the null space of the matrix is what you get when you try and treat the matrix as a set of linear equations equal to 0, and you can find that and it'll give you an answer. And the kernel of f is what you get when you try to find all the x's that make the answer come out to 0, and they turn out to be the same thing. It's the same collection of vectors that does both of these things. But if you're talking about the linear transformation, you have to call it a kernel. And if you talking about the matrix, you have to call it a null space. In the same way that humans have hands and cats have paws. It's the same thing, but when I'm thinking about it as different objects, I have to call it by a different name. That's the thing. And we also know that the range of F is the same as the column space of A. Yep. Which means that, yes, the range is the span of the columns of the matrix that makes the linear transformation. This is what's in my head. It's not really relevant, but it just helps to describe things. So I reckon there's going to be some thoughts and questions that people have, and I would like them to say them, please, at this point.
So would we calculate like the range and kernel the same as you would for the null space and col space?
Exactly. That's like, if you know what the matrix is that goes with your linear transformation, you do the calculation from the matrix. So one way of finding, you've got a linear transformation like F. One way of finding the kernel would be to find the matrix A and then do the RREF and do the free variables. Is that what you were sort of saying?
Yes, I think that, that makes sense.
If you didn't, still good. If you didn't have the matrix A already, you'd have to find it. It is sometimes possible to not use the matrix and to solve the equations directly. So for example, back here, this one here, you don't actually have to find the matrix first. You can just go, well, the kernel would be what you get the solutions to f of x equals 0. That's what that is. And so if this is 0, you'd need x plus y to be equal to 0 and 2y minus t to be equal to 0 and z plus t plus 5x to be equal to 0. And you could attempt to solve that directly and turn it into a matrix from there without technically finding the matrix first. So this would be cool. Oh, it's so cool. This would mean that t is 2y. This would mean that x is minus y. And this would mean that z is minus t minus 5x, which is minus 2y plus 5y. And so we have that x, y, z, t is minus y, y, minus 2y plus 5y, 2y, which is y times minus 1, 1, 3, 2. And ta-da, we have a basis. So you can find a basis to the kernel without going via the matrix if it looked obvious. Yeah. How do you feel about that?
I feel a lot better about that.
Oh, sorry, Vin.
Oh, sorry. You go.
I was just gonna say, when you talk about the matrix, do you mean like the standard matrix?
I do mean the standard matrix, but I forget to call it the standard matrix because there's only one.
Yeah. I was just making sure I was on the same page. That's all good.
So yeah, we call it the standard matrix as if there's non-standard matrices, but there aren't. Like if you can write it as a matrix, then that's the standard matrix. So The reason we call it the standard matrix is if we changed our coordinate system and we used different coordinates for all the points, then we would have to have a different matrix. Yeah, but we're not changing the coordinates. We're just keeping the vectors as they are. So, yeah. But yes, it is the standard matrix. But there is only one matrix that will work. If you can find a matrix that does it, it's guaranteed to be the standard matrix because there's only one. Yeah. So yeah, in my head, I go, well, there's only one. Why do I need the word standard? But yes, you should probably call it standard matrix if you're in your course. Okay. So one of the things that people who mark exams will get uptight about is using the right word in the right place. So if they ask about a linear transformation and they haven't mentioned the matrix A, then you need to tell them that you're going to call the standard matrix A. And when they ask you about a linear transformation's kernel, then you need to call it the kernel and don't call it a null space of F. It's the null space of the matrix. So it's just one of those things. Linear transformations have kernels and matrices have null spaces. Because technically a linear transformation isn't the matrix itself, it's the function that the matrix defines. So yeah, one of those little things. Yeah, we're very precise in maths about our language when we're writing.
Wait, the standard matrix is just the ones down the diagonal, isn't it? And the rest zeros. Isn't it?
No.
Oh?
That's the standard basis.
Oh, whoops, yeah.
So yeah. So the standard matrix is the matrix that does this trick. So if you can rewrite your thing as a matrix, then that's the standard matrix.
Oh, yeah. Okay.
And it is related to the standard basis. Like the standard basis is this.
Yeah. Okay.
That's the standard basis. And they are related, actually. If you do the linear transformation to the standard basis, then what you get is the standard matrix.
Yeah, that's right.
So if you do F on all of these things,
yeah,
and you get answers, then that matrix, that is the standard matrix.
Yeah, I get you, David. That's good.
I've never drawn that picture exactly that way before, and I like it.
Yeah, so do I.
Yeah. So, and that's the secret way of finding the standard matrix. Like some people you can find the standard matrix in other ways than this. If you find any way that you can think of that will rewrite your linear transformation as matrix times vector will produce the standard matrix. But if you can't think of a way to rewrite it, then this will always work. Yeah. So if your F is some wicked, stupid thing that says project it onto this and then rotate it and then do this, if you just do all those things to this vector, whatever the answer is the first column of the standard matrix.
Yeah, I think I get you.
Yeah.
Yeah.
So
yeah.
What we're butting up against here is that mathematics is not technically about procedures. It's about ideas, and we've got an idea of what a standard matrix is, and we've got some things that happen to be true about them, and that means that we now have multiple ways of finding it, and some of those ways are easier in some situations than in others. But we do have one way that will always work, but we have some other ways that are going to sometimes be faster. So yeah. Right. So that's basically it for linear transformations, except for there's a classic linear transformation problem that finds a standard matrix when you haven't been told what the function actually is, but all you've been told is what the function does to a couple of vectors. It's a classic problem, and I really feel like I should talk about it because, pardon me, I'm sure some people are going to want to know. So here we go. So this is all well and good. If you're given like a lovely formula or a description of what your linear transformation does, like this, then there's lots of ways to find the standard matrix. You could go, okay, well, f of x, y, z, t is x plus y, 2y minus t, z plus t plus 5x. That's great. And I would like to rewrite it as matrix times the original vector. And I can totally do this. This will be 1x and 1y and no z's and no t's, and 0 x's and 2 y's and no z's and minus 1 t's, and 1 z and 1 t and 5 x's and no y's. Ta-da, done. That's the standard matrix. That's how I would normally do it in this situation. But you could just as easily have done this. You know, f of 1, 0, 0, 0 is 1 plus 0, 2 times 0 minus 0, 0 plus 0 plus 5 times 1, which is 1, 0, 5, and that's the first column. And f of 0, 1, 0, 0 is 0 plus 1, 2 times 1 minus 0, 0 plus 0 plus 5 times 0, which is 0, 2, 0, and that's, 1, 2, 0, and that's the second column. And keeping on down that road, and it would slowly produce this matrix one column at a time, which is a very fabulous magic trick that linear transformations do. And those are two ways I could find that standard matrix. But what if you weren't even told what the formula was? What if, you know, and if you don't have a formula, but just a description of rotations and stuff, you could go, oh, well, it rotates this much, so it's going to be this new vector, and that's going to be the first column, and that's great. What if you weren't even told what the thing did? What if all you were told was just what it did to some vectors? So it's a classic problem to go, sorry, just a second. Yeah, that'll do. What if all you were told was this information? How would you find the standard matrix of that linear transformation? Feel free, there's a put your hand up or a tick button in the participants menu. So could you just give me a tick in the participants menu if you've seen a problem like this before? Yeah. So here's the thing. We don't have a formula. We can't figure this out without the formula, but we can if we can figure out what f of 1, 0, 0 is, and what f of 0, 1, 0 is, and what f of 0, 0, 1 is, then we'll be able to figure those three answers will be the columns of the matrix. And we do know that if we add the answers together, the inputs together, then that will add the answers together as well. So what we need to do is figure out how to create the vectors 1, 0, 0 and 0, 1, 0 and 0, 0, 1 out of these three vectors here. And there are many ways to do that. One way is to stare at them until you've got an answer. I do not like my chances. It's going to be not pretty. Don't like it at all. Yeah, I mean, you could just try it and go, if I add those two together, I'll get 3, 6, 10 instead of 3, 6, 0. So I could add those together and then take off this one, and that would give me 0, 0, 10. So I could go like 2, 5, 7 plus 1, 1, 3 is 3, 6, 10. And so that means that f of 3, 6, 10 should be f of 2, 5, 7 plus f of 1, 1, 3, which is 1, 8 plus 0 minus 1, which is 1, 7. And then f of, and then I know 0, 0, 10 is 3, 6, 10 minus 3, 6, 0. And so f of 0, 0, 10 should be the f for this, which was 1, 7, minus the f for this, which was 5, 2. And so that answers minus 4, 5. And so that means that f of 0, 0, 1 should be a tenth of that, which will be minus 0.4 and 0.5. And now I have the last column of the matrix, and I could continue just trying to combine them together in those ways until I got to figured out all three of the columns, and that would take a long time if the vectors weren't set up nicely. Okay, that's one way. The other way is to be extremely clever about it, or at least look clever. It's not actually, this is the coolest thing ever. I love this. So I would like to find some linear combination of these that produces 1, 0, 0. And if I did the same combination of these, it would be f of 1, 0, 0. So that's what I'd like to do. I want to two, 5, 7, and 1, 1, 3, and 3, 6, 0. Yeah. To produce 1, 0, 0, and 0, 1, 0, and 0, 0, 1. That's what I want to do. And then I want to do the same linear combinations of the outputs. That's what I want to do. If I could figure out some multiple of each of these that produced that answer, then the same multiple of each of these would produce whatever f of that is. That's the goal. Okay, and I know that row operations are the same as doing linear combinations. I know that. You know, adding two rows together, that's a linear combination. Multiplying a row by something, that's a linear combination. Swapping rows, that doesn't even count. And so I could do this. Finding linear combinations that get from these to these is the same as doing row operations that get to here. Like that. That's doing linear combinations. And if I want to do the exact same linear combinations on these vectors, that's okay. I'll just chuck them here. Because doing row operations, if I treat this as one big matrix, whatever I do to this, I'll have to do to that as well. So I'll do the same row operations. So by the time you get there, this will be f of 1, 0, 0, and this will be f of 0, 1, 0, and this will be f of 0, 0, 1. And so I'll transpose that, and it will be the standard matrix.
What made you originally put the vectors? So like you know how we've got the vectors 2, 5, 7, 1, 1, 3.
Yeah.
What made you put it as a row instead of as a column in some matrix?
So back in Math 1A, vectors were always columns, right?
Yeah.
And that's why you're asking this question. What made me put it as a row is because row operations do linear combinations.
Not column operations.
Yeah, I mean, column operations do linear combinations too, but we're not used to doing column operations.
Yeah, okay.
So if you were able to do column operations without just accidentally doing row operations, then go for it. You'd need this matrix, right, up that way. But it's much easier for us to do row operations, and computers are set up already to do row operations. And so I wrote them as rows so that the row operations did the linear combinations I was aiming for. So this is the reason why I wrote them as rows, because I know that row operations are linear combinations of rows.
Okay. And when you have the augmented side, so the thing on the right of it, would you almost treat that as like when you've got the elementary matrix, so whatever you change to the left, you also change to the right?
Exactly.
And then it becomes the final answer which you want.
Yep. And if you were asking your computer to do it, you would just enter this as one great big matrix. There wouldn't be a line there. It would just be the matrix 25718 1130 minus 136052. And you just tell it to row reduce that matrix and it would do the trick. It's a really cool process, but I warn you that if you're going to use it, you must provide this explanation first.
Yeah. Okay.
Because no one taught you a process for doing this in the course, and there are actually many different processes that could do it. And so you have
definitely seems like the best.
Yeah, but you have to say, I want to do linear combinations of these to produce these, and then do the same linear combinations of those. And then row operations are linear combinations of rows. So if we put the vectors as rows in a matrix, that will maintain the linear combinations we want. Yeah.
Speaking of row operations, in the exam for the written component, if we have to row reduce something and they don't specifically ask us to show Gauss-Jordan, can we put it in an online calculator and just spit it out?
As far as I know, if they don't explicitly tell you how to do it, then you are allowed to do it in whatever way you think is best. If they say you must show your row operations, then you must. But
what
if
about
they don't,
show all working?
Well, I think in Maths 1B, I think they're okay with you just saying this is the reduced row echelon form.
Yeah, cool. Thank you very much for
don't know for sure, but I'm pretty sure because I'm not involved in the School of Math. I'm not part of the School of Maths. I'm not involved in the decisions about the marking scheme or anything like that. I never get to see the exam ever because I'm not part of the school, so I don't know for sure. But I'm pretty sure that if they don't specify that you must show row operations, then it's okay not to, because the vibe of Maths 1B is what row operations are capable of doing for you and not the row operations themselves per se.
Yeah. Oh, good stuff. Thank you, David.
Yeah. But I will warn you that they're likely to give you things that have variables in them that you're just going to have to do it anyway.
Yeah.
Like they might give you a standard matrix that's got an A in it, like a and a B and a C, and say, well, what do A, B, and C have to be for this standard matrix to have kernel of dimension 2 or something? And then you've got no choice. You're going to have to do it by hand because that's all you've got.
Yep.
Yeah.
I've got a question about the transpose there.
Yep.
So that would be on that right-hand side.
Yep.
It would be 3 rows and I guess 2 columns. And then when you transpose that, it's just going to be 2 rows and 3 columns, right?
Yeah. Yes, it would. Yep. So this will be like 1, 2, 1, 2.
Yeah. Yeah.
1, 2, and this will be that way.
Perfect. Yeah. Just making sure.
Yeah. And the reason you transpose it is that to create the standard matrix, the vectors have to be written as columns.
Yeah.
And you've done a process that writes them as rows because that was convenient at the time, but you're going to have to write them as columns in order to be a standard matrix.
Mm-hmm. Cool.
Yeah.
Thanks.
Right. Well, I managed to talk about that for quite some time, actually. I didn't have time for ratio tests and that sort of thing. Well, I don't really need to apologize, but I feel bad for you, those who wanted to talk about ratio tests and Taylor series and things. But I will say to you that I have done revision seminars on those things in almost every semester in the past. So if you go have a check at the website, you'll be able to see those. And also, you can always come and talk to us at the Maths Learning Centre. So before I sign off, Does anyone have any things they want to say or ask about linear transformation stuff?
I did have a question, Dave. It was a while ago, though.
Yeah.
You were talking about like bases, and like you were trying to. You're talking about also column space and row space. It was on one of your pieces of paper there. Yeah, not that one, but there was something you said about. Can't really remember.
That's all right.
Or it could be. Yeah, no, I think it is. Yeah. Did you say that like the row space? You see that matrix you got there? So the 1078 thing. Yeah. So are you saying like if you take those two rows, the ones that you've highlighted, and they become the row space for the matrix A?
Yeah, they are the basis for the row space. Technically, the row space is the span of those.
Yeah. So okay, so you've gone A, you've row reduced it, and then you're saying those two vectors that you've highlighted there, those two, they become a basis for the row space.
Correct.
I'll just write that down, because it's probably good to have. Maybe it might come up, be useful.
So that's the same deal as what I was doing with my linear transformation there. I put them as rows, so that when I did row operations and I produced whatever I got at the end, the fact that I'm capable of producing these means that they are still in the row space, because I just did row operations which are linear combinations which don't change the row space. So yeah.
That's good, David. Yeah, so is it just so basically you get A, you row reduce A, then the rows which are not full of zeros, they become the vectors for a basis of the row space.
Correct. That was very correctly said, and no, it was correct and also said correctly.
Thank you. Yeah, appreciate that.
Well said, Dave. Well said.
Thanks, guys. Appreciate the support. It is tough learning this math stuff. So
yeah, that is what we're here for. So 80% of the visitors to the Maths Learning Centre are from Maths 1A or Maths 1B. So that's what we're here for, just to make sure that maths life is better with the maths you're studying at uni.
Yeah. I love the videos you've got on your website, David.
Yeah,
I've been using them a lot.
Thank you. That's why I keep them there, because if someone
I didn't actually see that that sheet that you showed earlier about the eigenvalues. I'm going to download that.
Yeah, they redid our website recently, and some of the stuff is gone, and you can't tell the difference just by looking at it of whether it's going to be a video or a handout. But I haven't been able to, because of this year, being able to fix any of that. So sorry about that, but it is there now. You know it's there.
Yeah, no, that's great.
Cool. Well, good luck, everyone. I'm going to sign off, and I wish you the best in the process of studying and doing your exam.
Yeah. Thanks, Dave.
Thanks, David.
You're welcome.
See you later.
See you, Dave.
Bye, everyone.